Hi, my name is Duncan Coutts and I'm the head of engineering for the Cardano project, and I'm going to talk in a bit more detail than I have in the past about some of the things we're doing with how we develop high assurance software for Cardano. So some of you might have read a blog post that I wrote some time ago now, describing in very general terms how we are planning to improve the assurance of the software that you write. So I'm just going to recap that slightly and explain what is high assurance, what does it mean, and why is it important. And then I'm going to go into maybe a bit more technical detail about some of the interesting things that we're working on right at the moment. There's a whole team that I'm overseeing, and we're doing some rather interesting and exciting stuff at the moment. And I'll try and describe, without getting into too many tricky technical details, but I'll do my best, what we're doing at the moment. So just to recap, what is high assurance and what does it mean and why should you care? So assurance is really about, can you be sure that the software that you're using is not going to fail? It's as simple as that. It's about, so think of it like this. Cryptocurrencies are important things. They have lots of money tied up in cryptocurrencies. People treat them as money, right? That's the whole point. So it's important that the system works, and it's important that you have confidence that the system will work. And these things are made with software, and as everybody knows, software is, in general, rather fallible. If you think just about how often software that you use has bugs, crashes, you wouldn't want that with the software that underlies your cryptocurrency. That would be really bad. And in fact, we've seen lots and lots of examples of this. I mean, you just have to look at the news in the cryptocurrency world for regular articles about failures to do with the software that runs the cryptocurrency. Sometimes that's smart contracts, other times it's other kinds of flaws. So it's important, if we as a community really believe that cryptocurrencies are for real, then it really is important that we take software assurance seriously. Because if we don't, we're not actually being serious about cryptocurrencies, right? So software assurance is about saying that this software, giving some evidence and degree of confidence to yourself, to everybody, that this software is going to work as it is intended to work, and doesn't have some kind of horrible flaw that would allow a hacker to exploit the system, bring it down, steal everybody's money, that kind of thing. So the more important what the software controls, the more important it is that the software is high assurance. So good examples of this are things like flight control systems in aircraft. That's really, really important. Life or death, that the software that controls how the aircraft behaves is correct, right? Otherwise, everyone on the plane is going to die. So there are existing practices in engineering of how to make high assurance software, but they tend to be very expensive. The software, the flight control example is a good example. That's a very expensive way of developing software to achieve those levels of assurance. And so for most ordinary commercial software, people don't do that. And because people don't do that, that is why most software is frankly not very good. That's why most software has bugs, has flaws, has security updates all the time. Just look at how many security updates there are in Windows or Mac OS or Android or all these things. It's not just operating systems, but all sorts of bits of software. They all are continuously having security updates. And why is that? It's because they had bugs in it in the first place. And perhaps you can fix the bugs before someone discovers them, exploit them, but often not. And what's better would be to say there are no bugs in this system, and to have some realistic evidence that is really true. So the question is, how can we achieve high assurance? Well, okay, first of all, there's different levels of assurance corresponding to different levels of confidence. If you've tested something a bit, maybe you're a bit confident that it doesn't have any bugs. But if you've tested it a lot, maybe you're more confident. Or maybe you can do better than testing, and you can do better than testing. So yes, in general, assurance, not to be confused with insurance, right? Assurance is is about establishing evidence that software does not have flaws, and it's the degree to which you have that amount of evidence. So, like I said, with the aircraft example, for that you want really high assurance because people are going to die otherwise. For ordinary commercial software, the assurance level is very low, and there are levels in between. So, my goal with Cardano is to improve the level of assurance. We're not going to hit at least not in the short term, we're not going to hit the level of assurance that you get in like the aircraft control systems, but we can certainly do better, and that's my goal. And the way that we're going to do that is to apply more computer science. Academic computer science knows how to do these things. They're just not typically done in most commercial software development because it's too expensive usually, or because people don't know how to do it, or inertia, or there's lots of reasons why people don't do it. But in my opinion, those are mostly excuses. And for things that are important, and we're putting a lot of money at stake, like cryptocurrencies, then we ought to do it, right? It's important that these systems don't fail. So there are two basic approaches to achieving high assurance. There's the kind of the traditional approach, which has been done since the 60s and 70s, and there's the kind of more modern sort of computer science-based approach. The traditional approach is to be very careful, and you gather evidence about how you make the software. Like you have to use lots of processes and ISO 9000 certifications, and you fill in lots of documents that says who did what and when, and it generates lots and lots of evidence about how you built the software, but it doesn't actually generate evidence about the software at the end, just the process by which you got there. And that's been the traditional approach because there was nothing that you could do that was any better. But academic computer scientists working since the 80s and even before that have been looking at how do you reason about programs, how do you use mathematics to reason about programs, to give you assurance, to understand and prove things about programs. And so that approach gives us a method where we can, instead of very carefully documenting how we built something, we can generate evidence that the final bit of software is actually correct. So we end up with some software and separately evidence in the form of like reasoned arguments, mathematical proofs, various different kinds, evidence about the final software that we produced. So in that sense, you don't need to know how the software was built, you just need to look at the final evidence about the software that was built. And that's kind of the distinction. And we're taking that latter approach, or moving in that direction. So what does that mean? So we're grabbing various bits of computer science, the bits that seem appropriate, that seem useful, and we're saying let's use those to help us develop our software in a much more rigorous way. So the thing about this approach is it treats software as mathematics. That's the key philosophy, that's the key insight. If you've ever written any programs yourself, you might be familiar with languages like C or Python or Java. And in these languages, they don't have this mathematical essence to them. They're really languages built by engineers to get stuff done, which is fine. But academic computer scientists looking at how to write programs and how to write programming languages, they look at these programs and they say, they're mathematical objects, and we can reason about them in the same way that you use algebra to reason about things in the real world, to reason about, all sorts of stuff. So the key thing is to say that programs are mathematical objects, and to use programming languages that make that easy, that are designed to help you reason about programs as mathematical objects. So a language like Haskell, which is what we're using to build Cardano, is a kind of language where it is inspired by mathematics. You can use mathematics to reason about what the program means, what it does. Is this program equivalent to that program? Things like that. So the key step is realize that programs are mathematics, and then use mathematics and mathematical techniques to reason about a program. And what do I mean by reason about it? I mean things like have a specification of a program in mathematics, in mathematical terms, and then to do things like proofs. You prove, and this is a proof in the ordinary mathematical sense of proof, right? So an honest-to-goodness mathematical proof, which can be completely sound, you can have complete confidence in. You can write proofs about whether your program meets its specification. That's kind of the Holy Grail. The Holy Grail is to say we have a specification, which we understand, that's a formal mathematical specification, and we have a program that is understandable in mathematical terms, and we can prove that this program meets this specification. That's kind of the ideal situation. And if we can do that, brilliant. I mean, that's easier said than done, but that's the overall picture. So what do I mean by specification for starters? Well, for example, if you think of a cryptocurrency, you might have a specification that consists of a set of properties. And one property might be there should be no double spending, right? That's a good property for a cryptocurrency. Or you might have a property that value is not created or destroyed through a sequence of transactions. That's a high-level property, and that's not necessarily a complete specification, but you might make up a specification out of a bunch of these properties, and then you would show that mathematically you would prove that this particular design of cryptocurrency meets that specification. For example, it might be possible to prove, and indeed I think people have proved this, that the UTXO style of accounting that comes from Bitcoin, and it's the same style that we use in Cardano, that the UTXO model of accounting does meet the properties of a cryptocurrency. It does, prevent double spending, and it does. And you knew that already, right? You already assumed, because Satoshi told us that the UTXO model should prevent double spending, and but that's an informal statement. Whereas this is a mathematical proof that is true, right? You thought it was true, but were you really sure that it was true? How sure were you that it was true? Well, if you have a complete formal mathematical proof that it's true, then you can sleep easy at night. That's the point. So, yeah, you can prove things which you thought were true and you thought were obvious, but now you know them for sure. And when you're doing things that are much more complicated, that really, really helps. Right? Okay, so maybe we should look at that's the general idea of proofs and reasoning about programs. Maybe let's turn to what are we doing at the moment. So as I said, we're not trying to reach really high assurance straight away. Right? We're going to do this step by step. We're going to improve the assurance, but it's not going to be high assurance, not in the sense of, like I said a moment ago, a complete formal mathematical proof, end-to-end, no ifs, no buts. What we'll do is we'll take particular chunks of the system and we'll do formal developments of those chunks of the system and then replace, let's take a brick out and replace it with a better brick, which we will have developed in a way that is higher assurance, but not necessarily high assurance, right? There's different, as I said before, there's different levels. But we're working towards that goal. So let's take a concrete case of a thing that we're working on right now. So as you know, Cardano is based on the Ouroboros blockchain protocol, right? This is the underlying consensus proof of stake protocol that's been developed by academic cryptographers. And so that is a starting point, right? So the academics, the cryptographers, they went away and they thought for a year, and they came up with Ouroboros. And they wrote an academic paper and they had it published. And they are mathematicians, cryptographers are mathematicians, and they made a formal proof that has been peer-reviewed by other people, other cryptographers, other mathematicians. They've done a proof that their Ouroboros protocol has certain properties. Like, remember I said earlier, you might have properties like no double spending or whatever. So for the blockchain protocol, the properties that they proved, it doesn't really matter for this case, but let me just state them anyway, it's interesting. Let's see, what are the properties? So one of them is that there's a progress property that, given certain assumptions, it's always possible, in fact, it's guaranteed that blocks will be produced. And there's also not immutability, a persistence property, that once blocks are of a certain depth in the chain, that they are stable, that they will not change under changes of like forking. Once they're a certain number deep, then the probability of them being forked is so low that it doesn't really matter. So those are the like two properties, and they proved mathematically that their protocol meets those properties, that it satisfies that, it has those properties. So that is our starting point for building the software implementation that implements Ouroboros. So what we are doing at the moment is we're doing a new implementation of Ouroboros. In fact, it's of Ouroboros Preos, which is basically the next version from the cryptographers. And so the point is that this mathematical specification that the academics, the cryptographers, has made is very high level. It's a very long way from the software. It describes what the protocol should do, but it's short and it's very dense and it's lots of mathematics, and it's a really long way from code, right? Similarly, it's like the difference between Satoshi's Bitcoin paper and the Bitcoin implementation in C. Those are just miles apart, right? And so it's very hard to say that, if you think of Satoshi's paper being a specification, it's not a formal specification, but it's a specification. And if you think of the Bitcoin C implementation being the code, they're so far apart that it's nigh on impossible to say that this code meets that specification. And so then we can't do the high assurance thing that I was talking about. What we really want is to be able to say, here's a mathematical specification and a mathematically understandable version of the code, and that these two things, one implements the other. The implementation satisfies the specification. But if those two things are so far apart, like with the Bitcoin example, then it's just impractical. You can't do that. So how are we trying to do it? Right? We've also starting with a mathematical specification. In this case, it's more formal than the Bitcoin one. The Bitcoin one is an informal specification. This one has proper mathematics in it. But we still need to get to code that runs. So how do we do it? Well, the idea is we start with the original spec and we refine it step by step. And what does that mean? We refine it towards working code. Right? So that means we start with the original specification and we make another version of the specification that is a bit more detailed, that fills in some details that are not described in the high-level version. Because the high-level version of the protocol that's described in the paper is so high level, it's almost unrecognizable. For example, everybody knows that blockchain protocols work by broadcasting blocks, right? That you send out a block and other people receive the block. But the way that the mathematical paper describes Ouroboros is it says you broadcast the entire chain. Now, it's not doing that because they're stupid and they think that that's a good idea. They know that. But it describes it that way because it makes the mathematics easier. And it's a model of what happens in the real world. But obviously, the real protocol has to work by broadcasting blocks. Now, you can't broadcast the entire chain. I mean, think of the size of the Bitcoin blockchain. It's, I don't know, how many gigabytes is it at the moment? You can't broadcast that in 20 seconds. It's nonsensical. But it's a useful mathematical model for proving that the protocol works. But it's a long way from what the code has to do, right? So the first step of our refinement is to say, well, let's go from a version of the mathematical specification that does things in terms of broadcasting whole chains, unrealistic, to something that works in terms of broadcasting blocks, slightly more realistic. There's still lots of things about it that are still unrealistic, or they still have details that have to be filled in. But it's now more realistic, right? That's one step along the road. And in fact, there'll be a whole series of these steps. And the point is, at each stage, we should be able to say that these two are morally equivalent, that they are the same in some way, that the version of our specification that broadcasts chains and the version that broadcasts blocks are morally the same, or even better, actually provably equivalent in some formal sense, in the sense that they achieve the same outcomes, they achieve the same, that each node ends up with the same chain locally as they would under the original version. So that's an example of a refinement. So the point is that our approach is not to say, here's the spec, here's the implementation, we will directly prove that the implementation meets the specification, because they're so far apart. So instead we say, let's take the original specification and refine it a bit, refine it again, refine it again, refine it again, and keep going. At each stage, we're making design decisions, etc., until we get to something that is low level enough that captures all the details of how the system has to really work. You know, it captures the details that we have to have a peer-to-peer network, that we have to work in bounded space. You know, you can't use arbitrary amounts of RAM for the system. That there are timing constraints, that things have to work using TCP. You know, all these kinds of details are not captured in the original high-level paper, but they have to be captured in the code because the code has to actually do those things. So by having this series of refinements, we get closer and closer to the code. Let me draw a diagram. So here's a diagram to explain what I mean and what we're doing, and go into a bit more detail. So I said a second ago that we have this mathematical paper that's written by the cryptographers, and that's an academic published paper, and it has lots of mathematics in it, but it's not code, right? Remember, it's maths and not code. And it's written by mathematicians, cryptographers, as I say, mathematicians, and I'm a computer scientist, and so I look at this paper, and I look at it in a different way to the way that the mathematicians look at it, me and my colleagues, and you know, we appreciate that it's got proper proofs in it, but we look at these kinds of things slightly differently and say, well, actually, that's really not as precise as we would like it, or it's not quite in the right form. We want to be able to reason about it in a different way. We want to use a different logical language for describing the protocol. And also, we aren't interested at this stage in the proofs of the properties of like progress and persistence that are preserved that are proved in the paper. We're interested in what does the protocol actually do, because we need to implement it, right? We need to implement that protocol, and then if we implement that protocol, of course, it'll have the properties that the guys say it will in the paper. So our first step is actually to translate their description of the protocol into our description of the protocol, which is in a different formalism, a different formal logical language. So this is why I say over here there's mathematicians, and over here is computer scientists, who are different kinds of mathematicians, if you like. And so we describe again what the protocol does, how it works. So we have a formal language that captures precisely captures the behavior, the meaning, how the protocol actually works, when people create blocks, all that kind of stuff. And then, so we've done that by reading the maths paper. And so we need to show, we need these two things to be equivalent, right? Our version, our description of the protocol, and their description of the protocol. And that's the first step. So we write this description, and we look at the maths and we say, well, we think that's right. And then we go and talk to the mathematicians and say, can you understand this? Does that correspond precisely to what you wrote in your paper? So this is a step that involves manual inspection, right? So this requires people like Agalos, who wrote the paper, and other of his co-authors, and other mathematicians and cryptographers who understand that and understand this to say, yes, these are the same. These describe precisely the same protocol. So that's step one, translating into a different language. And we use this thing called the psi calculus, which is a process calculus. So process calculus is a thing from computer science. It's this in the literature. It's been around for many years. There's lots of different ones. And these things are These are used to describe concurrency, concurrent systems and distributed systems. And what is a cryptocurrency, a blockchain protocol rather, if it's not a distributed system? It is a distributed system. So in principle, it seems like using a process calculus to describe the blockchain protocol is a perfect match. So we're using a particular formal language, this one called the psi calculus. And so what we have then is a description of Ouroboros, or Ouroboros Preos actually, in the psi calculus. And we think that is equivalent to the version that's in the paper. And it's our responsibility to demonstrate that to the mathematicians, so that they also believe that it's so that everybody has confidence that we're talking about the same thing, but in two different descriptions. And then from then on, we don't need to trust in like people understanding that two things are the same. We can then be a bit more formal from then on. So the idea is now that we do these refinement steps. So my diagram here sort of represents a series of refinements. And the reason this one's big at the bottom is because there's lots of detail in the one at the bottom. The ones at the top are still small, they're still very high level, they're very abstract. They don't go into lots of detail. They just say you broadcast entire chains, and it doesn't say how that works. Whereas down at the bottom, you've got working code ultimately, which is obviously very big, much bigger. And in between, you have a series of specifications. These things are still specifications, but they're becoming ever more detailed. So the first one is still not very detailed. It's equivalent to the original paper. And then as we go from one refinement to the next, so remember I said the first refinement we have to do is going from describing the protocol in terms of broadcasting entire blockchains in one go, as if that were possible, to doing it by broadcasting blocks, right, which is more realistic. It still doesn't say how you broadcast the block. It still doesn't talk about the peer-to-peer network and things like that, but it's one step along the road. It's more realistic. So that's what's represented here. And then in general, there's going to be a whole sequence of others. And we haven't, we're part way along the process at the moment. And then how do we, we're trying to show that these things are equivalent in a formal sense. Because remember, the final argument is going to be that our working code really does the same thing that the paper describes, right? That's the ultimate goal. And the evidence for that should be evidence that these things are equivalent to each other and equivalent to the original paper. And then if you put all that together, that is the evidence that our code implements what's in the paper, and the paper has a formal proof of its correctness. So that is our assurance story, right? And that's the evidence that we produce at the end about the thing that we've built, with all of these intermediate specifications as we went along. But it's worth noting that these intermediate specifications are not just there to produce the evidence that the thing we've done at the end is correct. They're also there for our benefit to help us design it, right? Because as we go from one step to the next, we're making design decisions. Like when we go from a step that talks about broadcasting blocks to a version that talks about broadcasting blocks using a particular peer-to-peer network, that is a design choice. How does that peer-to-peer network work? There's many different ways you could do it. And so when we do that refinement, we are at that stage making design choices. So this also helps us with our design process, and at each stage we can have confidence that we've done things correctly if we can show these kinds of equivalences. Now, we may not initially prove formally every single one, but we want to do this stuff in a way such that we could if we needed to, or maybe later we'll come back and do them all. So in particular, at the beginning, we're trying to at least formally prove this first one so that we can show that we can do it. So that, maybe we won't prove every single one, at the beginning, but so long as we know that we can do it, then we can come back and do it later. But even if we don't prove every single one, just the process of developing things in this style gives us a much higher confidence that we've done it correctly. It doesn't produce quite the same quality of evidence for everyone else, but it's still a much more reliable process than just build the final working code and hope that it's the same as the maths paper. So what does this kind of equivalence look like? So formally, we want something that says that if you are happy with this one, you would be happy with that one. So in particular, it's something like everything that this one can do, this one can do. And every state that this one can end up in corresponds to a state that this one could end up in. That's the kind of equivalence. And we can express that, every state, blah, blah, blah. We can express that kind of statement, that kind of property. We can express that formally in mathematics and logic. And we can try and use the logical language that goes along with psi-calculus to prove that kind of equivalence. So we're currently in the process of doing that, and we're exploring different ways, different tools, different ways of expressing these things and different ways of doing these kinds of proofs. One in particular that we're playing with at the moment is a formal proof system. You may or may not have ever heard of this. It's called Isabelle, and it's a very mature, existing, it's been around for decades now, system for encoding on a computer formal mathematical proofs. So it's a really sound system. So if you have an Isabelle proof of something, you're really sure it's true. I mean, it's even a higher level of confidence than you doing a proof on paper. And if you do a proof on paper, maybe you got it right, maybe you didn't. You need another human to go and check it. With a proof in Isabelle, the computer checks it, and the computer can tell if you've done it right. So we're experimenting with using Isabelle to prove these kinds of equivalences. And if we can do that, that's actually an extremely high level of assurance. I'm not guaranteeing we will get there for everything. It's an experiment at the moment, and I'm not saying that we will necessarily prove all of these using Isabelle, but we might do the most important ones, and we can always go back and do more of them later. So that's the idea. Another interesting thing here is that these aren't just specifications. These things actually work. These things are actually executable. Right? These are executable specifications. Even the first one, as I said, was very high level and sort of completely unrealistic in the way that it broadcasts entire chains. You can still run that in simulation. And that's actually extremely useful. Before you start to prove anything, proof takes a little while, and it's tricky, and it's difficult, it's time consuming. Before you start to prove something, you can test stuff. So if you can run this one, and you can run this one, and you can test that they seem to always do equivalent things, that they end up in equivalent states, then that's a good starting point for trying to prove that they always end up in equivalent states. Whereas if you run the tests, if you run these and they just do different things, we go, oh, well, I made a mistake. Let's try something else. So you can run all of these things in simulation. So all of them are working code. They just don't necessarily all run in a real network. They may only run in simulations. And the simulations will become more and more realistic as we go along. Until finally, there's not necessarily a big gap between the final specification and the working code. They can actually be the same thing, right? In computer science, the difference between a specification and working code, it's a very grey continuum. I mean, there's no hard barrier between the two. Programs can be specifications. Specifications can be programs. You can have specifications that are not executable, but an executable specification really is both. It runs, and it may not run very fast, but it runs, and it is a specification. As in, we can prove it's equivalent to something else, or things like that. So, if we follow this process in the way that I expect and I hope it'll go, it means that the final specification will actually be working code. It won't just be, we end up with a specification and now we toss it over the wall to a bunch of engineers who go and hack it up in Haskell. The final one will actually be code that actually runs in the system. And part of the way that we're doing that is that, because as you know, Cardano is implemented in Haskell. And what is this? This is psi-calculus. Well, that's not Haskell. Well, actually, we can make one be the other, basically, because we can embed psi-calculus in Haskell. And what does that mean? That means that so Haskell is very good for hosting other languages. There's this idea you may have come across, you may have heard of, called DSLs, domain-specific languages. And that's where you use a small language and you embed it inside a host language. And the embedded language is for doing one particular kind of task. Like in this case, it's for describing concurrent processes. But in other cases, it's for doing other things like describing probabilistic programs or describing logic backtracking programs or describing graphics compilators. There's all kinds of little DSLs. And they can be, and the idea of an embedded DSL, embedded domain-specific language, is that we can do one of those inside a host language. Examples of things that are not embedded would be things like SQL, you might say, is a domain-specific language, but it's not embedded inside any particular programming language. Whereas what we're doing here is we're saying we are taking the psi-calculus and we are embedding it inside Haskell. So our descriptions of the protocol are written in psi-calculus, but they're written in psi-calculus that is hosted within Haskell. And that's actually how we make them executable, because we simply have a Haskell interpreter or Haskell interpretation for the psi-calculus that runs it in simulation. And then the final one down here, it would still be psi-calculus in Haskell that we just run, that uses now TCP connections and all the rest of it. So that's the idea, that the final version will be still in the same style and the same language and the same sort of setting as all the previous specifications. And all of them can run in simulation, and at least the last one, should be able to run for real, if you like. So that was the story about how do we make sure that we end up with correct working code at the end. But correctness is not the only thing. I mean, when people talk about programs being correct, they usually mean that they achieve the right outcomes. The sort of functional correctness is what like testers talk about, or specifications. You talk about functional specifications, but there's also what people call non-functional requirements, and those are things like performance. And actually, of course, performance is very important here. I mean, in a blockchain protocol, it's important that blocks are received within a certain amount of time, that transactions make it into the system and are incorporated into blocks, and blocks get back to everybody in a certain amount of time, right? When you're using Cardano and Daedalus, and you create an ADA transaction, and you send it out, how long does it take for the person to receive it? Well, that's important. I mean, whatever time it takes, if it was 2 days, that would be useless, right? If it was 30 seconds, maybe that's brilliant. So performance requirements are really important. They are important requirements. So the normal sort of formal software development process often doesn't capture those non-functional requirements, the performance requirements. Or equivalently, there's things like how much memory does it use? Does it require a machine with gigabytes and gigabytes of memory, or will it run on your phone or your laptop? Or these are important questions. So one of the extra things that we're trying to do at the moment is to integrate performance modeling into this kind of process, and that is actually a very nice and interesting idea, and it's not something that I've done before. So that's quite exciting to me. We're working with some other experts who know all about this kind of particularly network performance modeling. In fact, there's some of the other videos on the Cardano website are interviews with those guys, the predictable network solution people. And they have a nice, again, mathematical model of performance, particularly performance for networking systems and protocols and things like that. And so at the moment, what we're trying to do is integrate their mathematical formalism for describing performance into our approach into this design methodology, so that we don't have to wait until we get to working code before we discover, oh, it's too slow, right? That would be terrible. I mean, the whole point of this kind of approach is that by the time we get to the end, we know it's going to work, because it's kind of correct at every stage along the way. But if it's only correct and not also performant, then we've missed an important part of the requirements. So the idea is, if we can integrate into this like psi-calculus formalism, a formalism that talks about the performance of the system, then we can be sure at the early stages of the design that we're not making any critical mistakes in our design that will cause us to miss our performance goals at the end. So we don't have to wait till we get down to here before discovering that we made a mistake back here. Right? We should be able to. The performance modeling should mean that we can tell at this stage, before we've done these bits, before we've expended all that effort, we can tell at this stage that we have made a wrong design choice, and we can make a different choice. Or it might mean that something's impossible and we've got to do something completely different. But before we've spent all the energy and effort and time of doing these later stages. So that one is another mathematical formalism. So this is a mathematical formalism about performance, and it's called the DeltaQ. We write it like this. That's just the name of the system, of the formalism. But what's it really about? It's about modeling how long do things take to happen, and do they happen, or do they fail to happen? Right. So it's a formalism that not only talks about performance, but it also talks about failure, and that's actually really important because real networks, the internet, they fail from time to time. Connections get lost, packets get dropped, electricity goes off, people trip over wires. Right. Failure is an ever-present possibility, and we have to deal with that as part of our performance modeling. So it's actually, it sounds all very complicated and algebraic, and it is all very algebraic, but the fundamental idea is very simple. So a DeltaQ is a probability distribution. So okay, I'll start off by drawing it like this, and this is time on this axis. So let's call that in seconds, let's say, or microseconds. Doesn't really matter. These are units of time along here, and so time goes that way, starting from 0. And this is 0 to 1 is the probability density. So what does this look like? Let's give an example. Let's call that, let's call this seconds, just to make things simpler. And we'll say that most of it sort of goes like this. Right, so this is an example of a probability density function where how do we interpret this? It says that the probability of something taking 2 seconds is that much. That's it. The probability of taking 2 seconds. The probability of taking 3 seconds is less. The probability, there's almost zero probability of it taking less than a second, and there's very little probability of it taking more than 3 seconds. Most of it is sort of bunched around here. So that's an example of a probability density function where most of it is kind of clumped around about one bit. Now, a different way of showing that same diagram in a way that's a bit easier or a bit more useful actually is to make it cumulative. So in this you've got there's 1 up here. This is because eventually if something is guaranteed to happen eventually, then it okay, so 0 down here and time this way again. So the equivalent here, this will only be approximate, but hopefully you'll get the idea. This will look like something that shoots up like that and then kind of tails off like that. So this is the again the time along here, and this is supposed to represent the same thing but in a different way. And this is saying after 3 seconds, what is the probability that it arrived before 3 seconds? And here we're saying it's almost 1, or maybe it's in fact exactly 1. So it's in this example, I've had it actually hitting the axis down here. So in this case, it's guaranteed to have happened by about 3 and a bit seconds, and thereafter it's just 1. Everything has happened before that. At this point, so if this is that's 0.5 halfway up. So this is saying that at least half the time, or exactly half the time, the probability is that it'll arrive, before whatever this point here is. There's a 50% chance of it happening before this point in time, and 50% afterwards. And so the rate at which it goes up is sort of the important thing, and where it gets to. So if you have an event like you send out a packet over the internet, and you're measuring how long does it take to get there. This is the kind of thing these things are used to measure. And the point is that you send out if I send a packet from here to there, how long does it take? Well, it's not always the same. I mean, people say, what's my ping time? Oh, my ping time is 50 milliseconds. But it's not really exactly 50 milliseconds, is it? It varies. So the way to do it is to look at it as a distribution. Well, sometimes you could look at the min and the max, but this is a much more precise way of describing that. But what if the packet never arrives? Right? What if it fails? Normal probability density functions and cumulative distributions here say that it must all add up to 1. But if that wouldn't be helpful for modeling failure. So what we do instead, and what the DeltaQ says, is that it doesn't actually have to add up to 1. You could have something where it never, so there's 1 at the top there, and it never gets there, right? So and this difference is the chance of failure, right? Of it never happening. It's failed. So like with a packet, sending out the packet and it just never gets there. And what's nice about that is it lets us model failure in the same description as we use to model the performance. How long does it take to get there? Or it may never get there at all, right? So a DeltaQ is one of these kinds of distributions, but it's actually much we can build it up in a much more algebraic way. I mean, the final interpretation is one of these sort of cumulative distributions here. but we can build it up in a much more algebraic way. So, for example, if I have, so let's just turn out. So if I have a process that does something and then it does something else, and supposing we have a distribution of how long that takes. Supposing this takes between 1 and 2 seconds, and it's randomly distributed. It's anywhere between 1 and 2 seconds with an uniform distribution between 1 and 2 seconds. Right? That's a simple example of something. And we had another one over here that takes between 2 and 3 seconds. But maybe this one's 1 and 2 seconds with a 0.5% chance of failure, for example. And this is between 2 and 3 seconds, but there's also a 2% chance of failure. So this is a DeltaQ. This is also a DeltaQ associated with doing this thing and associated with doing that thing. And we want to say, I'll do this one and then do that one. So this is sequential composition of actions, and each of them has a DeltaQ. Well, there is a way of producing the DeltaQ of the overall, of the composition. And this is really critical. I mean, being able to do this thing in a compositional way is really kind of the computer science approach to things is break things down, build systems build algebraic descriptions that are compositional, because that's what modularity is. You can't do these kinds of analysis unless it's modular. I mean, or you go insane. It just becomes too difficult. So this is a modular way of describing the performance of the system. We say, doing this, then doing that, and we have a DeltaQ of the one and DeltaQ of the other. And there is a so this is a if in an algebraic style, if we have the DeltaQ of A and the DeltaQ of B, the DeltaQ of A followed by B is something in particular, and there's a way of computing what that is, and it turns out it's a convolution. Doesn't really matter, but the point is that there's an algebraic description of the performance corresponding to what you're doing, and then we can look at this algebraic description of the performance and we can analyze that, and the whole point is then that we can compute the overall performance of the system based on the performance of the parts and how those parts interact. And that's the fundamental thing. So going back to the previous idea about the psi calculus and our specifications and refinements and stuff, the idea is if we can give a description of the blockchain protocol in the psi calculus, and we can describe how the parts of the description interact with each other and what the DeltaQs of different parts of it are, we can derive by this kind of algebraic method the performance, the DeltaQ, of the whole thing. For example, we could check, given certain assumptions about how fast the internet works or things like that, we could derive by looking at the way we've described the protocol. We could derive, for example, how long does an individual slot take? Like how quickly can we get a block from one slot leader to another? Can we do that in 20 seconds? Can we do it in 15 seconds? If we're trying to build the system to hit a certain slot length, then that's our target, and we want to be able to analyze that early on. So if we can build these kinds of performance models that say, yes, actually, given these assumptions, that should be possible, then as we refine it, we can check that we're still able to do that. And that we can then build a system that meets its performance goals. So the DeltaQ method, is an existing algebraic method, and we're working with experts who use this in analysis of real systems, particularly telecom systems. But what we're doing that's slightly new here is we're trying to integrate that with our functional correctness, our psi calculus descriptions, so that we can do both at the same time. And if we could do that, that's a really powerful method. It should enable us to build things with reasonably high assurance, and hopefully, and also with the performance that's required, and hopefully not take too long over it. Right? I mean, I said at the beginning that building high assurance systems for flight control software is phenomenally expensive, and there's a lot of effort. Well, if we can do this stuff right, then by making decisions early on and not having to make mistakes and go back and do it again, we might be able to do things so that it doesn't take quite as long as normal high assurance software development takes. So I'm reasonably hopeful that we can integrate these two things. We haven't done it yet, but we're getting closer to being able to integrate these two methods together, so that we can produce good quality software that meets its performance goals. So I'm pretty excited about this. And so this is the kind of thing that we want to do for not just Ouroboros, but other kinds of developments where correctness and performance are really important. So there'll be other parts of the system that we eventually apply this kind of method to. So I think that just about covers that. I hope that's not been too technical or too hand wavy. If you're interested in further details of this kind of stuff, I'm sure we can provide some links. Okay, well, thank you very much.